A star is born every second somewhere in the universe, but on Earth, recreating even a fragment of that fire has already consumed decades of research and billions of dollars. Fusion promises electricity from hydrogen, no runaway chain reaction, and fuel drawn partly from water. Yet behind that promise lies a harsher reality: plasma hotter than the sun, scarce tritium, neutron-damaged walls, colossal magnets, and machines that may cost more than the power they ever produce. Is fusion the doorway to a new energy age, or the most elegant scientific gamble in history? A like subscription or share helps this kind of calm science storytelling reach more curious minds. Thank you for spending this time here. One quiet question belongs in the comments: what time is it there, and where in the world is this being heard? Now, the magnetic fields are rising, the plasma is beginning to glow, and the long experiment can begin. Energy is the quiet foundation beneath nearly every human system. Every modern society depends on a steady flow of it. Yet every major source comes with limits. Fossil fuels release stored sunlight from ancient life, but they also fill the atmosphere with gases that alter the climate and with pollutants that damage health. Nuclear fission can produce immense amounts of electricity from small quantities of fuel, but it leaves radioactive material that must be handled with care for long periods. Against this imperfect landscape, nuclear fusion appears almost impossibly attractive. It offers the vision of drawing power from the same basic process that causes the sun and the stars to shine, using fuels that seem abundant, producing no carbon dioxide during operation, and avoiding the kind of runaway chain reaction associated with a damaged fission reactor. The idea sounds less like a new machine than a correction to the energy problem itself, as though nature has already demonstrated the ideal power source and humanity only needs to learn how to copy it. That promise has shaped scientific ambition for generations, yet the same promise has also become a symbol of delay. Fusion has often seemed close enough to justify the next experiment and distant enough to remain beyond commercial reach. The central mystery is not whether fusion can happen. It happens constantly across the universe, and it has been produced many times in laboratories on Earth. The harder question is whether it can happen in a controlled machine, for long enough, often enough, and cheaply enough to deliver dependable electricity to a power grid. That difference separates a scientific breakthrough from an energy revolution. The sun does not face this distinction. Its vast gravity presses matter inward, creating a core where hydrogen nuclei move fast enough and remain confined long enough for some of them to fuse. The process converts a small part of their mass into energy, and that energy slowly travels outward before escaping as heat and light. On Earth, there is no stellar mass available to provide confinement. A reactor must replace gravity with engineering. It must create fuel hotter than the center of the sun, hold that fuel away from ordinary walls, control instabilities that can develop in fractions of a moment, survive bombardment by energetic particles, and turn released heat into electricity without consuming more power than the facility can produce. Together, they form one of the most demanding technological projects ever attempted. The basic reaction is simple to describe. Light atomic nuclei join to form a heavier nucleus, releasing energy because the final products have slightly less mass than the original fuel. But the nuclei carry positive electrical charge, and positive charges repel one another. Before fusion can occur, the particles must approach closely enough for the strong nuclear force to bind them. That requires extreme speed, which in a fuel appears as extreme temperature. At such temperatures, atoms no longer remain intact. Their electrons separate from their nuclei, forming plasma, a restless state of matter shaped by electric and magnetic forces. It twists, ripples, leaks, cools, and pushes against every attempt to confine it. The machine must therefore manage something that cannot touch its container in the ordinary sense. It must hold a miniature region of stellar conditions inside equipment built from materials that would be destroyed instantly by direct contact. Superconducting magnets may be cooled to temperatures only a few degrees above absolute zero, while plasma nearby reaches tens of millions of degrees. Lasers may deliver enormous power in a brief pulse to crush a fuel capsule smaller than a grain of pepper. All of this is required not merely to create fusion once, but to make it repeatable, maintainable, and useful. The dream survives because the possible reward remains extraordinary. The most tractable fusion fuels are forms of hydrogen. Deuterium, which contains one proton and one neutron, exists naturally in water. Tritium, which contains one proton and two neutrons, is rare and radioactive, but it reacts more readily with deuterium than many alternative fuels. When deuterium and tritium fuse, they form helium and release a fast neutron carrying most of the energy. In a future power plant, that neutron would strike a surrounding blanket, deposit heat, and help produce more tritium from lithium. The heat would then drive a turbine or another conversion system to generate electricity. The difference lies in the furnace. Instead of burning fuel or splitting heavy atoms, it would maintain a controlled plasma in which light nuclei occasionally unite. Supporters see in this process a path toward energy security measured not in years of reserves but in geological abundance. A failure of confinement would not lead to an accelerating reaction. The plasma would expand, cool, and stop fusing. This gives fusion an important safety advantage, but not a perfect one. Tritium can escape and enter water. Neutrons can alter and weaken structural materials. Components can become radioactive and require remote maintenance. A commercial plant would still be a major nuclear facility with complex hazards, strict regulation, and expensive systems of protection. The promise is cleaner and potentially safer energy, not energy without consequences. The tension becomes sharper when cost enters the picture. Fusion experiments are not ordinary power stations waiting for a final switch to be turned. They are scientific instruments designed to answer questions about plasma behavior, materials, fuel cycles, and reactor control. This often creates confusion. A machine may achieve a meaningful gain within the fuel, while the full facility still uses far more energy than it releases. A burst of fusion may prove that ignition is possible, while saying little about whether capsules can be manufactured, fired, and replaced at acceptable cost. Every milestone can be real and important without being the final milestone that public language sometimes suggests. Fusion therefore develops through layers of success. First comes the ability to produce the reaction. Then comes the ability to release more fusion energy than reaches the fuel. Beyond that lies the ability to produce more energy than the entire machine consumes. Beyond that lies the ability to turn the output into electricity. Beyond that lies reliability, maintenance, fuel supply, regulation, construction speed, and a price that can compete with technologies already improving. The distance between these layers is the space where the argument over fusion lives. Optimists see a sequence of solvable engineering challenges. Skeptics see a chain in which failure at any link can prevent commercial success. Both views begin from the same facts. Fusion is physically possible. Controlled fusion has been achieved. Important experiments continue to demonstrate progress. No fusion power plant yet supplies routine electricity to the grid. The question is how to interpret the gap. Fusion could belong to either pattern. Its future may depend not on a single dramatic event but on thousands of quieter advances in magnets, lasers, robotics, neutron-resistant alloys, tritium breeding, plasma prediction, and industrial production. A breakthrough may arrive as a machine that crosses a famous energy threshold. but a power industry emerges only when the entire system works together. That is why fusion can be described at once as one of the clearest scientific opportunities and one of the largest financial wagers. Governments and companies spend billions because the reward could reshape the energy economy for centuries. The same money could also support grids, storage, renewables, efficiency, advanced fission, and other technologies already delivering power. Fusion research therefore competes not only against physics, but against time, climate change, rising electricity demand, and the retirement of old infrastructure are immediate pressures. A reactor that works too late, costs too much, or cannot be built rapidly may have limited influence even if it proves scientifically magnificent. Yet abandoning the effort carries its own risk. The dream of fusion endures because it sits at the boundary between necessity and imagination. It asks whether the forces that sustain the stars can be brought into ordinary service without losing control of the conditions that make them possible. It offers abundance, but only through machines of extraordinary precision. It promises safety, but still creates radiation, waste, and industrial danger. It suggests simple fuels, but depends on scarce tritium and complex breeding systems. It appears almost limitless, but every practical step is constrained by materials, money, and time. The question is no longer whether a miniature star can exist on Earth for a moment. It already can. The deeper question is whether that moment can be transformed into a stable, repeatable, affordable source of power, and whether the long pursuit represents the beginning of a new energy age or one of the most expensive lessons in the history of science. At the heart of fusion lies a collision that ordinary matter strongly resists. Atomic nuclei carry positive electric charge, and like charges push apart. The closer two nuclei come, the stronger that repulsion becomes. Under familiar conditions, the barrier is overwhelming. Hydrogen atoms can drift beside one another for ages without their nuclei ever approaching closely enough to join. Fusion begins only when matter is driven into a state where enormous numbers of nuclei move with such speed that a small fraction can press through the electrical barrier. That requirement is the first reason fusion is difficult on Earth. The reaction itself is brief, but preparing the conditions for it demands temperatures so high that ordinary gases no longer remain ordinary. Electrons are stripped from atoms, leaving a mixture of free electrons and exposed nuclei. This mixture is plasma, a state of matter that behaves less like a quiet gas and more like a restless electrical fluid. Plasma carries currents, responds to magnetic fields, forms waves, develops turbulence, and can lose heat through paths that are hard to predict. In a fusion machine, the fuel is therefore not simply hot, it is electrically active, constantly moving, and always seeking a way to escape the conditions that make fusion possible. The need for extreme heat follows from the speed of the nuclei. Temperature is a measure of the average motion within matter, so heating the fuel gives the nuclei more kinetic energy. Most collisions still fail. The particles approach, repel, and scatter apart. Yet the distribution of speeds is uneven. Some nuclei move much faster than the average, and those faster particles have the best chance of reaching the tiny distances where the strong nuclear force takes over. This force acts across an extremely short range, but once two suitable nuclei come close enough, it can bind them together despite their electrical repulsion. Fusion is therefore governed by a narrow transition. At larger distances, the electric force keeps nuclei apart. At very small distances, the strong force can hold them together. The reactor must create enough high-speed encounters for that transition to happen often enough to release useful power. In the most widely pursued reaction, one nucleus of deuterium meets one nucleus of tritium. Deuterium is a heavy form of hydrogen with one proton and one neutron. Tritium is another form of hydrogen with one proton and two neutrons. When they fuse, they form a helium nucleus containing two protons and two neutrons, while one additional neutron flies away at great speed. The products do not contain quite as much mass as the original fuel. The missing mass has been converted into energy. In deuterium and tritium fusion, most of the released energy is carried by the fast neutron, while the helium nucleus remains electrically charged and continues moving within the plasma. That division shapes the entire design of a fusion reactor. The charged helium nucleus can help heat the plasma from within, supporting further reactions. The neutron, however, is not controlled by magnetic fields because it carries no electric charge. It escapes the plasma and strikes the surrounding structure, where its energy must be captured as heat. Before those engineering problems arise, the reaction rate itself must become high enough. A fusion plasma is not judged only by temperature, it must also be dense enough and confined for long enough. These three conditions are closely connected. If the plasma is very hot but too thin, nuclei rarely collide. If it is dense but loses heat immediately, the reaction fades. If it remains confined but never reaches sufficient temperature, the electrical barrier continues to dominate. Fusion depends on the combined balance of heat, density, and confinement time. Different reactor concepts pursue that balance in different ways. Magnetic confinement keeps the plasma relatively thin but aims to hold it for a much longer period. Inertial confinement compresses fuel to very high density for an extremely brief moment. Each method tries to satisfy the same underlying requirement through a different path. This explains why a laboratory can achieve fusion without approaching a practical power plant. A small number of reactions can occur under conditions that are scientifically valuable but energetically insignificant. Yet useful power demands far more than evidence that nuclei fused. It demands enough reactions to produce a large energy output. And it demands that the system maintain or repeat those reactions without consuming even more energy elsewhere. A gain inside the fuel can be a major achievement, while the complete facility remains far from net electrical production. Around the plasma, every supporting system must also succeed. Magnets or lasers require power. Fuel must be prepared with precision. Vacuum equipment must keep unwanted matter away, and cooling systems must carry the released heat toward a generator. A weakness anywhere in that chain can erase the apparent gain created at the center. The physics also contains a subtle advantage that prevents the electrical barrier from being completely absolute. Nuclei behave according to quantum mechanics, and quantum particles do not always follow the simple boundaries expected from everyday objects. Even when a nucleus does not appear to have enough energy to cross the electrical barrier in the classical sense, there is a small chance that it can pass through by quantum tunneling. It is essential in stars, where the core of the Sun is hot but not hot enough for large numbers of nuclei to overcome the barrier by ordinary motion alone. On Earth, tunneling also contributes to the reaction rate, but it does not remove the need for extreme conditions. It merely makes the impossible slightly more probable. And a reactor must turn that small probability into a sustained flow of energy. The plasma then faces another problem. Heating it creates pressure, and pressure encourages expansion. The hotter the particles become, the more strongly they spread outward. In a star, gravity pushes back. In a terrestrial reactor, something else must provide confinement. Magnetic fields can guide charged particles along curved paths, reducing direct contact with material walls. Rapid compression can use the inertia of a tiny fuel pellet to hold it together for a fraction of a moment. Both approaches are attempts to create a temporary substitute for stellar gravity. Its plasma survives only while the machine actively maintains that balance. If the fuel cools, spreads out, or becomes contaminated, the reaction rate falls rapidly. The same fragility that makes fusion safer also makes it difficult to use. The reactor must remain close to conditions that are extreme enough for fusion but stable enough for control. Even small disturbances can reduce performance. Impurities from the wall can enter the plasma and radiate heat away. Turbulence can transport energy outward faster than expected. Instabilities can distort the plasma, causing sudden losses of confinement. The effort to achieve fusion is therefore not simply an effort to reach a high temperature. It is an effort to organize a hot, electrically active, constantly shifting medium so that its useful reactions outpace its many routes of energy loss. When the balance is favorable, fusion power rises rapidly because hotter fuel produces more energetic collisions and more successful encounters. The helium products add heat, creating the possibility of a self-heated plasma in which the reaction helps maintain its own temperature. This condition is often described as burning plasma. It marks a change from a plasma heated mainly by external machines to one heated significantly by its own fusion products. Yet even this is not the same as a commercial power plant. A burning plasma still requires confinement, fuel control, heat extraction, material survival, and a complete energy system around it. The microscopic event remains the source, but the machine determines whether that source becomes useful. Fusion thus begins with a simple meeting of light nuclei and expands into a problem of extraordinary scale. A barrier measured across tiny atomic distances leads to magnets the size of buildings, lasers of immense power, cryogenic systems, precision fuel targets, and materials designed to endure neutron damage. The energy comes from a minute difference in mass, but reaching that difference requires control over matter at its most extreme. Every successful fusion reaction proves that the barrier can be crossed. The larger challenge is to make those rare crossings happen in vast numbers, inside a system that can survive them, capture their energy, and repeat the process without collapse. The mystery is not hidden in the nucleus alone. It lies in whether a reaction that nature allows so readily inside stars can be made orderly, continuous, and economical inside a machine built on Earth. Stars hold an advantage that no laboratory can reproduce directly. They are made from so much matter that gravity becomes a furnace. A star does not need walls, magnets, or lasers to keep its fuel together. Its own mass pulls every layer inward, and the weight of the outer regions presses down on the core. There, matter becomes compressed, temperatures rise, and hydrogen nuclei move fast enough for fusion to begin. It is a long balance between inward gravity and outward pressure, maintained across millions or billions of years. Gravity tries to collapse the star. Heat and radiation from fusion push outward. As long as those forces remain balanced, the star shines. This natural arrangement gives stellar fusion a stability that Earth-based machines struggle to imitate. The Sun contains more than enough mass to keep its core dense and hot without any external structure. Its gravity acts in every direction at once, continuously confining the plasma. A terrestrial reactor has none of this help. It must create conditions comparable to those inside a star while working with a quantity of fuel small enough to fit inside a building. Nature uses mass. Engineering must use precision. The center of the Sun is enormously hot, but not as hot as many fusion plasmas created on Earth. This may seem surprising until the role of density and time becomes clear. Solar plasma is held under immense pressure and remains confined for vast periods. Even though individual fusion reactions are rare, the Sun contains an almost unimaginable number of particles. A small reaction rate across such a large volume still produces a continuous flood of energy. The Sun can afford to be slow. A power plant cannot. A reactor must generate a useful amount of fusion from far less fuel and within a much shorter time. To compensate, it usually raises the temperature well above that of the solar core, increasing the speed of the nuclei and the chance that collisions will lead to fusion. Earth therefore does not copy the Sun exactly. It attempts to create a different route to the same nuclear result. The Sun mainly fuses ordinary hydrogen through a sequence of reactions known as the proton-proton chain. That process begins when two protons interact. But the first step is extraordinarily unlikely because it depends on the weak nuclear force. This slow beginning is one reason the Sun burns gently rather than rapidly exhausting its fuel. It is also one reason ordinary hydrogen is not the preferred fuel for early fusion power plants. A terrestrial reactor needs a reaction that occurs far more readily. Deuterium and tritium provide that advantage. Their nuclei can fuse at lower temperatures and at much higher rates than ordinary hydrogen under achievable conditions. Even then, the plasma must become hotter than the solar core because a reactor lacks the Sun's density, scale, and confinement time. Both rely on fusion, but the surrounding environments are radically different. Inside a star, gravity is the container, and the container cannot melt. On Earth, the plasma exists near materials that can erode, crack, contaminate the fuel, or become damaged by radiation. A star does not need to protect superconducting magnets from heat. It does not need pumps to maintain a vacuum, machines to inject fuel, or turbines to convert released energy into electricity. A reactor must control every stage. It must create the fuel mixture, heat it, confine it, remove waste products, capture energy, protect its structure, and repeat the cycle while remaining economical. Gravity performs many of these roles in a star without moving parts. The difficulty of replacing gravity becomes clearest when plasma behavior is considered. Charged particles move freely along magnetic field lines and spiral around them, allowing magnetic systems to guide the fuel away from solid surfaces. Yet magnetic confinement does not press inward as simply or uniformly as gravity. The field must be shaped with great care, and the plasma itself generates electric currents and magnetic effects that can distort the intended structure. Waves and instabilities grow within it. Some carry heat toward the edge. Others can shift the entire plasma or cause sudden losses of confinement. The machine must detect these changes and respond quickly. In a star, local disturbances occur, but the overwhelming mass maintains the broader confinement. In a reactor, a small instability can end the useful pulse. Inertial confinement takes another path. Instead of holding a plasma for a long time, it compresses a tiny capsule so rapidly that the fuel begins to fuse before it can fly apart. The capsule's own inertia acts as a temporary container. Powerful laser beams strike the target, its outer surface expands, and the inward reaction compresses the fuel. For a fraction of a moment, density and temperature rise sharply. If the compression is symmetrical enough and the central region ignites, fusion energy can spread into surrounding fuel. The method avoids the need for long confinement, but it replaces that problem with extreme demands on precision. Tiny imperfections in the capsule, uneven laser energy, or asymmetry in the compression can prevent ignition. Gravity does not need to strike a target evenly from separate directions. It already surrounds the core. Stellar fusion also benefits from patience. The Sun changes slowly because its fuel supply is enormous and its reaction rate is naturally regulated. If the core heats slightly, pressure rises, the core expands, and the temperature can fall. If the core cools, gravity compresses it more strongly, raising the temperature again. This feedback helps stabilize the star. A fusion reactor has no equally simple self-correcting balance. Its control systems must manage heating, fueling, confinement, and energy losses actively. A plasma can move from productive conditions to failure very quickly. The reaction may stop safely, but the goal of steady power disappears with it. The challenge is to hold the machine within a narrow operating range where enough reactions occur and damaging instabilities remain under control. The sun also handles energy differently. Energy produced in the core takes a very long time to work its way outward, repeatedly interacting with dense matter before reaching the surface. A power plant cannot wait for such a slow release. It must capture energy promptly and transfer it into a usable system. In deuterium and tritium fusion, fast neutrons leave the plasma and strike a surrounding blanket. That blanket must absorb their energy, withstand damage, and help create new tritium. The reactor therefore depends on materials performing tasks that stellar mass makes unnecessary. These materials sit close to one of the harshest artificial environments on Earth, where high heat, intense radiation, and repeated stress act together. The gap between a star and a machine is not only a matter of temperature, it is a matter of endurance. A star can lose particles, produce turbulence, and change shape while remaining a star. A reactor must operate within strict limits. Its magnets, walls, cooling systems, fuel cycle, and control software all depend on one another. A fault in one part can halt the entire process. This makes fusion engineering a study in substitution. Magnetic fields substitute for gravity. External heaters substitute for gravitational compression. Fuel injection substitutes for the vast reservoir of stellar hydrogen. Neutron blankets substitute for the surrounding mass that absorbs fusion energy. Robotic maintenance substitutes for the star's ability to continue without repair. Each substitution must work well enough that the whole system remains productive. This is why progress in plasma physics can be genuine while commercial fusion remains distant. The core reaction may become better understood, yet the machine around it still has to replace an entire star's natural architecture with manufactured parts. The star has no concern for efficiency in the human sense. It does not pay for magnets, replace damaged components, or compete with solar panels and wind turbines. It simply follows gravity and nuclear physics. A reactor must satisfy physics and economics at the same time. It must compress the work of stellar mass into a controlled chamber, accelerate a naturally slow process, and produce electricity at a cost society can accept. The task is audacious because it attempts not merely to reproduce fusion, but to outperform nature in speed, control, and usefulness. The sun gains its advantage from scales so immense that mistakes become minor fluctuations. Fusion machines operate at a scale where tiny errors can decide the outcome. Their promise depends on overcoming that imbalance. Every experiment is therefore an effort to replace the quiet pressure of a star with a more delicate form of order, one created not by gravity, but by fields, light, materials, and control. The question that follows is whether that artificial order can become durable enough to move beyond the laboratory, or whether the star's effortless advantage will always remain larger than the machines built to imitate it. Magnetic confinement begins from a simple fact about plasma. Because its particles carry electric charge, their motion can be influenced by magnetic fields. A charged particle moving through a magnetic field does not travel in a straight line. It curves, spiraling around the field line while continuing to move along it. This behavior offers a way to guide plasma without allowing it to touch ordinary material. Instead of placing the fuel inside a solid container, a magnetic reactor attempts to create an invisible cage, one shaped by carefully arranged coils and powerful currents. The most familiar version of this idea is the tokamak, a machine built around a chamber shaped like a thick ring. The word comes from an early description of a toroidal chamber with magnetic coils, and the geometry reflects a practical need. If a plasma were confined in a straight magnetic tube, particles would escape from the ends. Bending the tube into a closed loop removes those open exits. Yet closing the path introduces new complications, because the magnetic field becomes stronger on the inner side of the ring and weaker on the outer side. Particles drift, currents form, and the plasma begins to behave in ways that a simple circular field cannot fully control. The tokamak answers this by combining several magnetic fields. Large external coils create a field that runs around the long direction of the torus. An electric current driven through the plasma creates another field around the shorter direction. Together, these fields twist into a helical structure, wrapping around the chamber like invisible threads. Charged particles follow these twisted paths, reducing their tendency to wander outward. The plasma is not motionless inside this structure. It circulates, vibrates, and develops complex patterns. But the magnetic geometry gives it enough order to remain away from the walls for a useful period. That period may last only seconds or minutes in an experiment. Yet it represents a remarkable achievement. The plasma can reach temperatures far beyond the melting point of any known material, while floating only a short distance from solid surfaces. This separation is never perfect. Some particles escape from the magnetic field and strike the walls. Others travel towards specially designed regions where heat and impurities are removed. The machine must accept controlled losses while preventing sudden, uncontrolled ones. At the lower part of many tokamaks sits a component called the diverter. It acts as an exhaust system for the plasma edge, guiding escaping particles towards surfaces built to handle intense heat. The diverter removes helium produced by fusion, along with impurities that would otherwise cool the fuel. It also carries one of the hardest burdens in the entire reactor. Heat flowing through a narrow region can become concentrated enough to damage materials quickly. A successful magnetic fusion plant must therefore confine the core while managing the edge, because a plasma that remains hot in the center can still destroy its surroundings if the exhaust is not controlled. Creating the magnetic cage requires enormous engineering. The coils must produce strong and precisely shaped fields, and many advanced designs rely on superconductors. A superconductor can carry electric current with almost no resistance when cooled below a critical temperature. This allows magnets to operate continuously without wasting vast amounts of power as heat. Yet the result is an extreme contrast. The superconducting coils may sit near temperatures only a few degrees above absolute zero, while the plasma inside reaches tens of millions of degrees. Between them stand layers of vacuum, thermal shielding, structural support, and radiation protection. If too much heat reaches the magnets, superconductivity can be lost. The current then encounters resistance. The magnet heats rapidly, and the system must shut down safely. The magnets are therefore powerful and delicate at the same time. Heating the plasma requires more than the electric current that helps shape it. At first, the current itself can warm the fuel through electrical resistance, much as a wire heats when current passes through it. But as the plasma grows hotter, its resistance falls, making this method less effective. Additional heating systems then become necessary. Beams of fast neutral atoms can be injected into the plasma. Because the atoms carry no net charge, they can cross the magnetic field before collisions ionize them and transfer their energy to the fuel. Radio waves tuned to the motion of electrons or ions can also deliver energy, causing selected particles to absorb power. These methods push the plasma toward fusion conditions, but they consume electricity and add complexity. A commercial reactor must eventually rely heavily on heat from its own fusion products. especially the charged helium nuclei that remain trapped in the magnetic field. Until that self-heating becomes strong enough, the machine remains dependent on external support. The tokamaks plasma current creates another limitation. In many designs, the current is induced like the current in the secondary winding of a transformer. A central magnetic coil changes its field, driving current around the plasma ring. This process works naturally in pulses because the transformer cannot increase its magnetic flux forever. Once the available change is used, the pulse must end or other system must sustain the current. A power station, however, benefits from continuous operation. Starting and stopping a burning plasma places stress on components and reduces the time available for producing electricity. Researchers therefore study ways to drive the current without relying entirely on transformer action. Radio frequency systems and injected particle beams can help, while carefully shaped pressure gradients may allow the plasma to generate part of the current itself. Achieving steady operation remains one of the central goals of magnetic confinement. The plasma also resists control through instabilities. Some are small and constant, producing turbulence that carries heat outward. Others can grow rapidly and distort the entire plasma. A severe event called a disruption can cause the plasma current and stored energy to collapse in a short time. The released heat and electromagnetic forces can damage internal components. Fast electrons may also form powerful beams that strike the wall. Modern tokamaks use sensors, magnetic controls, fuel injection, and predictive software to detect dangerous conditions and respond before they become severe. Pellets of frozen gas or other material can be injected to spread the plasma energy during an emergency shutdown, yet avoidance remains better than mitigation. A commercial reactor must operate for long periods without frequent disruptions, because even events that do not destroy the machine can reduce component life and increase maintenance. There is another magnetic approach that avoids the large plasma current of the tokamak. The stellarator creates most of its twisted magnetic field through intricately shaped external coils. In principle, this allows continuous operation with fewer current-driven instabilities. In practice, the geometry becomes extraordinarily complex. Coils curve in 3 dimensions. Manufacturing tolerances become demanding, and the magnetic field must be optimized to keep particles from drifting outward. Tokamaks have historically achieved stronger plasma performance, while stellarators offer potential advantages in steady operation and stability. Both belong to the same larger idea: the plasma is held not by matter, but by a carefully designed landscape of magnetic force. Magnetic confinement has advanced because each generation of machines reveals more about plasma behavior. Larger devices can reach higher temperatures and longer confinement, while improved magnets and control systems bring the conditions closer to those required for self-heating fusion. Yet size alone does not solve every problem. A larger reactor stores more energy, making failures more serious. It exposes broader surfaces to neutron damage and heat. It becomes more expensive to build and slower to modify. The path toward magnetic fusion therefore depends on balance. The machine must be large enough for good confinement but practical enough to construct. Its magnets must be strong enough to hold the plasma but reliable enough for continuous service. Its walls must survive the escaping heat, and its fuel cycle must replace tritium as it is consumed. A tokamak can create a plasma that looks almost weightless, suspended in darkness by fields that cannot be seen. Around that quiet ring, however, stands an immense structure of steel, superconductors, pumps, heaters, diagnostics, shielding, and control equipment. The apparent simplicity of a glowing loop hides the scale of the effort required to keep it alive. Magnetic confinement is therefore both elegant and severe. It uses one of the fundamental properties of charged matter to avoid direct contact with impossible heat. Yet every improvement in confinement raises the demands placed on the surrounding machine. The plasma may be held away from the wall, but its neutrons cannot be held. Its heat may be controlled, but never eliminated. Its instabilities may be predicted, but not ignored. The magnetic cage does not solve fusion in a single act. It creates a narrow region in which fusion has a chance to become steady, and the future of the tokamak depends on whether that region can be maintained long enough for the entire power system to become more than an experiment. Laser-driven fusion takes a path almost opposite to magnetic confinement. Instead of holding a hot plasma for a long time, it tries to create fusion so quickly that the fuel begins to burn before it has time to escape. The method is called inertial confinement because the fuel's own inertia briefly resists its expansion. The target is usually a tiny capsule containing deuterium and tritium, often frozen into a thin layer around an inner cavity. Around it sits a larger structure designed to receive an intense burst of laser light. In a fraction of a moment, energy that would normally be spread across a large machine is concentrated onto an object smaller than a seed. The aim is not simply to heat the capsule, it is to crush it inward with extraordinary symmetry, raising the fuel to immense density and temperature while keeping the central region stable enough for fusion to begin. The sequence starts when many laser beams strike the target from carefully chosen directions. In some designs, the beams hit the capsule directly. In others, they enter a hollow chamber called a hohlraum and strike its inner walls. The chamber converts the laser light into a bath of X-rays, which surrounds the fuel capsule more evenly than the original beams could. These X-rays heat the capsule's outer surface so rapidly that the surface material explodes outward. By conservation of momentum, the rest of the capsule is driven inward. The effect resembles a rocket in reverse. Material rushing away from the outside creates an inward force that compresses the fuel at the center. The capsule does not merely shrink, its outer layers accelerate inward at enormous speed, and the fuel becomes far denser than an ordinary solid. Near the center, a small hotspot forms. If that hotspot reaches the right combination of temperature, pressure, and confinement, fusion reactions release energetic helium nuclei. These charged products deposit their energy nearby, heating more fuel and causing additional reactions. This process can become a brief form of self-heating. When enough of the fuel burns because of energy produced by fusion itself, the event is described as ignition. The word carries enormous symbolic weight, because ignition marks a transition from an externally heated target to one in which the fusion reaction contributes strongly to its own continuation. Yet the continuation lasts for only a tiny fraction of a second. The capsule burns and disassembles almost immediately. Inertial confinement does not try to prevent that ending. It tries to release enough energy before the ending arrives. The difficulty lies in making the collapse nearly perfect. A capsule may appear smooth, but microscopic defects can grow as it implodes. Slight variations in thickness, density, surface finish, or laser energy can distort the compression. One side may move faster than another. Small ripples can expand into larger fingers of material that mix cold outer layers into the hot center. This mixing lowers the temperature and weakens the reaction. The implosion must therefore be controlled with a precision that is difficult even to measure. Hundreds of variables influence the result, including laser timing, beam alignment, capsule shape, material composition, fuel purity, and the geometry of the surrounding chamber. The target must remain cold enough for the fuel layer to stay evenly frozen before the shot, then endure a sudden transformation into one of the hottest and densest environments created on Earth. The lasers themselves face severe demands. They must deliver energy in a pulse whose shape is carefully programmed over an extremely short interval. Too much power too early can destroy the capsule before proper compression begins. Too little power at a critical moment can leave the fuel too cool or too uneven. The beams must arrive with closely matched timing and intensity, because small differences can imprint asymmetries onto the target. Even after the pulse is designed correctly, not all of the laser energy reaches the fuel. Some is lost in the optical system, some in the hull ROM, and some in the outer layers of the capsule. The energy delivered to the target is therefore only one part of the energy consumed by the facility. This distinction became especially important when inertial fusion experiments began producing more fusion energy than the laser energy that directly struck the target. Such an achievement is scientifically profound, but it does not mean that the entire facility produces net electricity. The lasers may require far more energy from the electrical grid than they deliver inside the target chamber. Cooling equipment, target preparation, diagnostics, vacuum systems, and support machinery add further demand. A useful power plant must exceed the energy cost of the complete system, not only the energy absorbed by a capsule. It must then convert the released fusion energy into electricity, replace the target, restore the chamber, and repeat the process rapidly. A laboratory can spend hours preparing for a single shot. A power station would need to fire many times each second for long periods. That difference transforms inertial fusion from a physics experiment into an industrial challenge. Each target would have to be manufactured with extreme precision at very low cost. It would need to contain the correct amount of deuterium and tritium, remain cryogenically stable, and enter the target chamber at exactly the right position and orientation. Lasers would have to track and strike it with exceptional accuracy, while operating repeatedly rather than in isolated pulses. Optical components would need to survive constant stress. The chamber would have to handle heat, neutron radiation, debris, and shock without requiring frequent interruption. A system that succeeds once under ideal conditions may still be far from one that succeeds billions of times as part of ordinary operation. The fuel cycle adds another layer. Tritium is scarce, so a future plant cannot rely on a large natural supply. The chamber would likely need a blanket containing lithium to produce new tritium when fusion neutrons strike it. That tritium would then have to be recovered, purified, and loaded into new targets. Because the targets are destroyed in every shot, the fuel cycle would operate as a continuous manufacturing process. The plant would not resemble a single reactor vessel quietly burning for months. It would resemble a highly automated factory built around a chamber where tiny artificial stars appear and vanish in rapid succession. The appeal of this method is clear. Inertial confinement can reach extraordinary density, and it avoids some of the long-duration plasma instabilities found in magnetic systems. The burning event is so brief that the plasma does not need to remain stable for seconds or minutes. Each target is a fresh beginning. A failure in one shot does not necessarily ruin the next. The pulse-based design may also offer ways to separate the fusion event from delicate equipment, because the lasers can deliver energy from a distance. Yet the same pulse structure creates relentless repetition. A magnetic reactor attempts to keep one plasma under control. An inertial reactor would attempt to create, compress, ignite, and replace a new plasma again and again. Its challenge is not only achieving a powerful shot, but transforming exquisite precision into routine manufacturing. The chamber must recover quickly after every event. Debris must not cloud the next laser pulse. The inner surfaces must withstand repeated exposure to neutrons and radiation. The heat from many small explosions must be captured smoothly enough to drive an electrical system. The lasers must become far more efficient, durable, and rapid than those used in many research facilities. None of these requirements violates known physics, but together they create a narrow path toward commercial success. The importance of ignition is therefore real and limited at the same time. It proves that carefully compressed fuel can enter a regime where fusion heating becomes dominant within the target. It gives researchers a new experimental world in which burning plasma can be studied under conditions different from those in a tokamak. It validates years of work on capsule design, laser control, and implosion physics. But ignition is not a finished reactor. It is the opening of another stage. The question shifts from whether a single capsule can produce a meaningful burst of fusion to whether an entire plant can manufacture targets, deliver energy, capture heat, breed fuel, and repeat the event at a cost the electrical market can bear. Laser fusion concentrates the dream of fusion into a tiny moment. For an instant, a capsule collapses, a central spark appears, a nuclear reaction spread through fuel that did not exist in that state a heartbeat earlier. Then the structure vanishes. The scientific achievement lies in creating that instant. The engineering challenge lies in making the instant ordinary. Until that happens, inertial confinement remains both a breakthrough and a warning nature may permit the star-like event. While industry still has to learn how to summon it again and again, without allowing the cost of precision to consume the energy it creates. A fusion experiment can cross a famous threshold and still remain far from producing useful electricity. This is not a contradiction. It is a consequence of where the measurement begins and ends. Inside a fusion target or plasma, scientists may compare the energy delivered directly to the fuel with the energy released by fusion reactions. If the fusion output exceeds that immediate input, the result can be described as a gain. In some cases, the fuel may even enter a self-heating state in which its own fusion products provide enough energy to sustain further reactions for a brief period. These are genuine milestones. They show that the central physics is working more effectively than before. Yet a power plant is not only a region of burning fuel, it is an entire chain of machines, each consuming energy, losing energy, and adding demands that do not appear in the narrowest laboratory calculation. The difference between ignition and electricity begins with this boundary. A scientific experiment often isolates one part of the system so that the behavior of the fuel can be understood clearly. A commercial plant must include everything. The magnets must be energized. The lasers must be charged. Pumps must create vacuum. Cryogenic systems must cool superconductors or frozen fuel. Heaters must bring plasma to reaction conditions. Control systems must monitor instabilities. Cooling loops must carry heat away. Fuel must be purified, injected, recovered, and replaced. Turbines or other generators must convert thermal energy into electrical power. Every step introduces inefficiency. A reactor can therefore produce more energy within the fusion event than reaches the fuel, while the full facility still draws far more electricity from the grid than it returns. The phrase net energy becomes meaningful only when the boundary is defined. At the smallest boundary, it may refer to energy entering and leaving the fuel. At a wider boundary, it may include the driver that heats or compresses the fuel. Wider still, it may include all supporting equipment. For an actual power station, the relevant measure is the electricity exported after the plant has supplied its own needs. Until that final boundary is crossed, fusion remains an energy experiment rather than an energy source. This layered accounting is especially visible in laser-driven fusion. A capsule may release more fusion energy than the laser light that strikes it, but the lasers themselves are not perfectly efficient. Producing a powerful laser pulse can require much more electrical energy than the pulse carries. Some of that energy becomes heat inside the laser system and must be removed. Optical components absorb small fractions and gradually degrade. The target chamber requires vacuum, cooling, shielding, and diagnostics. A single successful shot can therefore demonstrate ignition without approaching plant-level gain. The result answers a profound question about the fuel while leaving a separate question about the machine unresolved. Magnetic confinement faces a similar divide. A tokamak may produce a large amount of fusion energy during a pulse, but external heating systems, current drive, magnets, pumps, and cryogenic equipment consume power. Superconducting magnets reduce resistance, yet the systems that cool them operate continuously. Neutral beam injectors and radio frequency heaters lose energy during conversion and delivery. Even if the plasma becomes strongly self-heated, the plant must keep the magnetic cage stable and the surrounding machinery alive. The achievement of a burning plasma is therefore a crucial step, but it is not the final balance sheet. The released fusion energy also does not emerge as electricity. In the deuterium and tritium reaction, most of it leaves the plasma in the form of fast neutrons. These neutrons strike a surrounding blanket and transfer their motion into heat. That heat must then warm a working fluid, produce steam, or drive another conversion cycle, and turn a generator. Each stage loses part of the original energy. Thermal power plants cannot convert all heat into electricity, because some energy must be rejected to a colder environment. This is not a flaw unique to fusion. It is a general limit of heat engines, but it means the reactor must produce substantially more thermal energy than the electrical output it hopes to deliver. The internal systems then take their share before any electricity reaches the grid. A plant with a modest plasma gain may therefore have no exportable power at all. To become practical, fusion needs a margin large enough to survive every conversion loss and every internal demand. This is why a single ratio can mislead when presented without context. A gain greater than 1 may sound like the machine has become a power source, but that depends on what the ratio measures. If it compares fusion energy only with energy absorbed by the fuel, it excludes many losses. If it compares fusion heat with total heating power delivered to the plasma, it still excludes the inefficiency of producing that heating power. If it compares gross electrical generation with the plant's internal electrical consumption, it finally approaches the question that matters to a utility. Even then, the plant must operate reliably over time. A moment of positive electrical output has limited value if the machine requires long pauses, repairs, or preparation between pulses. Commercial energy is measured not only by peak performance but by availability. A power station must produce electricity through days, months, and years. It must survive repeated thermal cycles, radiation exposure, and mechanical stress. Its components must be replaceable on schedules that do not erase its economic value. Fuel must remain available. Waste heat must be removed. Unplanned shutdowns must be rare. The distinction between a laboratory record and a power system therefore includes time. An experiment may optimize one extraordinary event. A utility must optimize routine operation. This creates a difficult transition in design. Research devices often contain extensive diagnostic equipment, flexible controls, and access points that help scientists understand what happened. A commercial reactor would need fewer interruptions, stronger shielding, automated maintenance, and systems built for repetition. The machine that discovers the right plasma conditions may not be the machine that sells electricity. Its purpose is to reveal the laws and limits that later designs must use. This is common in technological history, but fusion makes the gap unusually wide because the experimental environment is so extreme. The plant must not only scale up performance, but it must also simplify, harden, and industrialize it. Ignition is best understood as the moment when the fuel begins to contribute significantly to its own heating. It shows that the reaction can move beyond complete dependence on external energy at the microscopic level. In a magnetically confined plasma, energetic helium nuclei can remain trapped and heat the surrounding fuel. In an inertial target, they can deposit energy within the compressed material and spread the burn. In both cases, the fuel crosses into a more autonomous state, yet this autonomy is local and temporary. It does not power the pumps, cool the magnets, manufacture the targets, or repair the walls. The reactor outside the plasma still depends on a much larger infrastructure. That is why ignition is both a breakthrough and a beginning. It removes one uncertainty while exposing the next. Once the fuel can burn, the question becomes whether the surrounding system can harvest the burn efficiently enough. Then comes the question of repetition, then durability, then cost. Fusion progress often appears slow because each success reveals another boundary. Before controlled reactions were achieved, the challenge was to make nuclei fuse. Once they did, the challenge became better confinement. As confinement improved, the focus moved towards self-heating. As self-heating becomes more credible, attention shifts toward materials, tritium breeding, heat extraction, and plant efficiency. This does not mean earlier milestones were empty. It means fusion is a system problem in which no single achievement can replace the rest. The final machine must satisfy all conditions at once. The central reaction may be the most dramatic part, but the quiet machinery around it determines whether the energy becomes useful. A reactor could produce spectacular bursts and still fail as a business. It could achieve strong plasma gain and still consume too much electricity. It could export power and still fail if components wear out too quickly. It could operate reliably and still lose to cheaper technologies. Real electricity begins only when physics, engineering, operations, and economics close the same loop. Until then, fusion remains a sequence of partial victories. Each victory narrows the uncertainty, but none alone answers the question implied by a light switch. The true breakthrough will not be a pulse that briefly releases more energy than one carefully chosen input. It will be a plant that starts, runs, survives, breeds its fuel, captures its heat, powers itself, and sends dependable electricity outward. That threshold is far less dramatic than ignition, but it is the threshold on which the entire promise depends. Fusion is often described as an energy source fueled by water, and the phrase contains both truth and concealment. One of the main fuels, deuterium, is a form of hydrogen found naturally in water. Every deuterium nucleus contains one proton and one neutron, making it heavier than the most common form of hydrogen. It is rare compared with ordinary hydrogen, but the oceans contain an immense total quantity, because the oceans themselves are immense. Deuterium can be separated from water through established industrial methods, and its abundance gives fusion part of its reputation as a nearly limitless source of energy. Yet the most achievable fusion reaction does not use deuterium alone. It pairs deuterium with tritium, another form of hydrogen that contains one proton and two neutrons. Tritium reacts with deuterium more readily than most other fusion fuels, allowing useful reaction rates at temperatures lower than those required by alternatives. That advantage makes it central to the leading reactor designs. It also creates one of fusion's least visible problems, because tritium is not abundant in nature, does not remain stable for long periods, and cannot simply be collected from seawater in the quantities a future industry would need. Tritium is radioactive. One of its neutrons eventually changes into a proton, transforming the nucleus into helium. Because this decay occurs steadily, any stock of tritium shrinks with time. Natural processes create small amounts in the upper atmosphere when cosmic radiation interacts with gases. but these amounts are far too limited for a large fusion economy. Most available tritium has historically come from specialized nuclear systems, especially reactors that produce it as a byproduct or for military purposes. This means the fuel often presented as part of an abundant hydrogen cycle begins with a scarce and carefully controlled material. A future fusion plant cannot depend forever on existing supplies. It must create much of its own tritium while it operates. The basic plan relies on lithium. When a neutron from deuterium and tritium fusion strikes certain forms of lithium, nuclear reactions can produce tritium. A reactor may therefore surround the plasma with a blanket containing lithium. The blanket serves several roles at once. It absorbs the energy of fast neutrons, converts that energy into heat, shields external components, and breeds new tritium to replace the fuel consumed in the plasma. On paper, this closes the cycle. Deuterium comes from water, lithium comes from terrestrial resources, and neutrons from fusion create the tritium needed for later reactions. In practice, every part of this cycle must work with high efficiency because tritium losses occur at many points. Some fuel passes through the plasma without fusing, some remains trapped in surfaces, some leaks into processing systems, some decays while stored, some is lost during maintenance or purification. The reactor must breed enough tritium not only to replace what fuses, but also to cover all of these losses and build an operating reserve. A plant that barely replaces the tritium consumed at the center may still run short because the rest of the fuel cycle is never perfect. This creates a narrow requirement known as the breeding margin. The blanket must produce more tritium than the reactor burns, and it must do so consistently under real operating conditions. Models can estimate how neutrons move through lithium, steel, coolant, shielding, and structural gaps. But the final performance depends on the complete machine. Openings for heating systems, maintenance ports, diagnostics, and fuel equipment interrupt the blanket. Materials absorb neutrons that might otherwise breed tritium. Some neutrons escape. Others lose energy before reaching the right lithium nucleus. The blanket must therefore be designed with extraordinary care, because a small shortfall repeated over months could gradually stop the plant. Tritium handling is also difficult because hydrogen can move through materials in ways that heavier substances cannot. Tritium atoms can enter metals, become trapped in microscopic defects, or pass through barriers under certain conditions. They can exchange with ordinary hydrogen and form tritiated water, which behaves chemically much like normal water while carrying radioactivity. This makes containment more complicated than storing a solid fuel pellet or a sealed metal rod. Pipes, pumps, valves, heat exchangers, and processing equipment must be designed to limit escape and recover fuel efficiently. The total amount circulating at any moment may be small compared with the mass of fuels used in fossil power stations, but the material is valuable, radioactive, and essential. Every gram matters to the operation of the plant. The fuel must also be delivered to the plasma in a controlled way. In a magnetic reactor, deuterium and tritium may enter as gas, as fast neutral beams, or as frozen pellets fired into the hot fuel. Most particles do not fuse during a single pass. They move through the plasma, reach the edge, and enter exhaust systems. The plant must separate unburned deuterium and tritium from helium ash and other impurities, purify them, and send them back. This recycling loop must operate continuously while keeping the plasma composition within a narrow range. Too little fuel reduces the reaction rate. Too much can cool or destabilize the plasma. Impurities can radiate energy away. Helium created by fusion must leave the core without carrying excessive amounts of useful fuel with it. The reactor therefore depends on precise control not only of heat and magnetic fields, but also of a fuel inventory moving through several physical states. In inertial confinement, the challenge takes another form. Each tiny target must contain a carefully prepared layer of deuterium and tritium. The fuel may need to be frozen into an extremely smooth arrangement before the target enters the chamber. A commercial plant would consume and destroy these capsules continuously, requiring an automated factory that can fill, cool, inspect, transport, and inject them at high speed. Tritium would pass through manufacturing lines as well as the reactor chamber, creating more places where it could become trapped or lost. A single successful capsule can be prepared with exceptional care. A power station must prepare vast numbers with the same precision while keeping the fuel cycle closed. Alternative reactions appear to offer escape from this difficulty. Deuterium can fuse with deuterium, producing either tritium and a proton or helium-3 and a neutron. Helium-3 can fuse with deuterium and produce charged particles with fewer direct neutron problems. Boron can fuse with protons under certain conditions and release energy mainly through charged products. These reactions are attractive because they may reduce neutron damage or dependence on tritium, yet they require much higher temperatures or produce lower reaction rates under achievable conditions. Some also create neutrons through side reactions. A fuel may look cleaner after ignition but be far harder to ignite. The easiest reaction brings the hardest fuel cycle. The cleaner reactions demand a plasma that is even more extreme. Helium-3 is often presented as a fuel that might be mined from the moon, where solar wind particles have become implanted in the surface over immense time. The idea has inspired visions of lunar extraction and a new energy economy beyond Earth. Yet the concentration is low, the mining scale would be enormous, and the deuterium and helium-3 reaction remains more demanding than deuterium and tritium fusion. Lunar helium-3 is therefore not a simple substitute waiting to be collected. It is a possible fuel for a more advanced stage of fusion, one that would require both a space mining industry and reactors capable of conditions beyond those now targeted by most projects. Its appeal reveals how quickly fusion's fuel story can move from abundance into speculation. The near-term path remains tied to tritium. This does not make fusion impossible, but it changes the meaning of its promise. The energy does not come from an ordinary cup of water alone. It comes from a carefully managed partnership between deuterium, tritium, lithium, neutron transport, chemical processing, and containment. Water provides one half of the leading reaction. The reactor must manufacture the other half. That requirement turns fuel from a background assumption into a central engineering system. A fusion plant may be able to stop its plasma safely in moments. Yet it cannot operate at all if its tritium inventory declines. It may have enough deuterium for ages, yet still depend on a breeding blanket that has never been demonstrated at full commercial scale. The apparent contrast is striking. Fusion is called nearly limitless because its basic elements are widespread, but its practical fuel cycle must be closed with extraordinary precision. The abundance lies in nature. The scarcity lies in the form that the machine can use. Whether fusion becomes an enduring power source may depend as much on recovering, breeding, and protecting a few kilograms of radioactive hydrogen as on producing the plasma itself. The star-like reaction sits at the center, but the future of the reactor may be decided in the quieter machinery that feeds it. A fusion reactor cannot depend on tritium arriving forever from an external stockpile. The available supply is too small. Its radioactive decay continually reduces what has been stored, and a commercial industry would consume far more than present sources can provide. The leading answer is to make tritium inside the reactor itself. This changes the fusion plant from a machine that merely burns fuel into a machine that must also manufacture one of its own essential ingredients. Around the plasma, beyond the vacuum chamber and close to the paths of escaping neutrons, Future designs place a thick region known as the breeding blanket. The blanket must capture the energy carried by fusion neutrons, convert that energy into useful heat, shield magnets and other equipment from radiation, survive intense bombardment, and expose enough lithium to enough neutrons that new tritium is produced faster than old tritium is consumed. If any one of these functions falls short, the entire reactor may lose either its fuel supply, its structural life, or its ability to generate electricity. The blanket therefore sits between the glowing plasma and the practical world of pipes, turbines, magnets, and maintenance. It is where nuclear physics becomes a fuel factory. In deuterium and tritium fusion, most of the released energy leaves the plasma inside a fast neutron. Because the neutron has no electric charge, magnetic fields cannot confine it. It passes outward and strikes surrounding matter. That escape is a problem for plasma heating, but it is also the path by which the reactor can harvest energy and create new fuel. Certain lithium nuclei can react with these neutrons and produce tritium. By combining lithium with materials that slow, scatter, or multiply neutrons, engineers can shape the blanket so that more useful reactions occur. The objective is not simply to produce some tritium. The reactor must produce more than it burns. The difference between production and consumption must cover losses throughout the plant and provide enough reserve for startup, processing delays, maintenance, and decay. This requirement is often expressed through the tritium breeding ratio. A ratio equal to 1 would mean that every atom consumed is replaced in theory. In practice, that would not be enough. Some tritium remains trapped in surfaces, some is held inside processing equipment, some is lost during transfer, some decays before returning to the plasma. A working plant needs a margin above simple replacement, and that margin may be difficult to achieve once the real geometry of the reactor is included. The plasma chamber cannot be surrounded by a perfect, unbroken shell of lithium. Openings are required for heating beams, radio waves, diagnostics, fueling systems, vacuum pumps, and maintenance access. Structural supports occupy space. Coolant channels interrupt the breeding material, steel, shielding, and other components absorb or deflect neutrons. Every gap is a place where a neutron may escape without creating tritium. Computer models can follow these paths in great detail, but the final result depends on a physical machine with joints, ports, imperfections, and changing materials. A design that breeds enough tritium in an ideal model may fall below the required margin after all practical features are added. The blanket must also extract heat. When neutrons strike matter, their kinetic energy becomes thermal motion. A coolant flowing through the blanket carries this heat away toward a power conversion system. Possible coolants include water, helium gas, liquid metals, and molten salts. Each choice changes the chemistry, pressure, pumping power, safety case, and tritium recovery process. A coolant that transfers heat well may corrode structures. A fluid that tolerates radiation may be difficult to pump. A material that breeds tritium efficiently may trap it or release it too slowly. The blanket is therefore not a single substance. It is a carefully arranged system of breeders, coolants, structural metals, neutron multipliers, barriers, and extraction equipment. These parts must work together while occupying limited space close to the plasma. One proposed approach uses ceramic compounds containing lithium. Another uses liquid mixtures containing lithium, sometimes combined with metals or salts that can act as both breeder and coolant. A flowing liquid can transport heat and may allow tritium to be extracted continuously, but it introduces its own challenges. Strong magnetic fields can resist the motion of electrically conducting liquids, increasing pumping difficulty and creating uneven flow. Chemical reactions between the liquid and structural materials can cause corrosion. No blanket concept avoids complexity. Each rearranges the difficulties. Tritium must leave the breeding material soon after it's created. If it remains trapped, it cannot return to the fuel cycle, and the total radioactive inventory inside the machine grows. Extraction systems must separate tritium from coolants, gases, metals, salts, water, and impurities without releasing it to the environment. Because tritium is a form of hydrogen, it can move through tiny pathways in materials, exchange with ordinary hydrogen, and form tritiated water. Barriers may slow this movement, but radiation and heat can change those barriers over time. Seals age, metals develop defects, surfaces become damaged. The fuel factory must therefore remain closed even as the materials forming it are altered by the very neutrons that make breeding possible. The blanket also protects the magnets. Superconducting coils are among the most valuable and sensitive parts of many magnetic fusion designs. Neutrons and gamma radiation can heat them, damage insulation, and degrade superconducting materials. A thick blanket and additional shielding reduce this exposure, but every added layer increases the size of the machine and places the plasma farther from the magnets that shape it. Stronger fields may then be needed, increasing forces on the coils and supporting structure. Once again, one solution creates another demand. The blanket must be thick enough to capture neutrons and breed fuel, yet compact enough that the reactor remains practical. It must contain openings, yet not so many that breeding collapses. It must run hot enough for efficient electricity generation, yet not so hot that materials weaken or tritium escapes too easily. Testing such a system is difficult because no existing fusion power plant produces the same continuous neutron environment expected in commercial operation. Individual materials can be exposed to radiation in other facilities, and smaller experiments can study tritium release, corrosion, and heat transfer. Yet the full blanket must combine all these effects at once. Neutrons change atomic structures, create gases within metals, cause swelling, and make some components radioactive. Repeated heating and cooling produces mechanical stress. Coolants place pressure on channels. Magnetic forces act during operation and shutdown. Tritium passes through the system while maintenance access remains limited. The blanket may be divided into modules that can be removed by remote machines, but replacement interrupts power production and adds cost. A design that breeds fuel successfully, but requires frequent replacement may still fail economically. The startup problem makes tritium even more important. A new plant needs an initial inventory before it can begin breeding its own fuel. If many reactors are built, each one requires enough tritium to start while earlier plants must continue operating. The growth of a fusion industry could therefore be limited by how quickly existing reactors create surplus fuel. A plant that breeds only slightly more than it consumes may sustain itself, but contribute little to the startup of the next plant. Expansion would be slow. A higher breeding margin could accelerate growth. But achieving that margin demands more blanket volume, better neutron use, lower losses, and faster processing. The fuel cycle becomes not only a technical constraint but also a limit on how rapidly fusion can spread. This creates a quiet paradox beneath the vision of limitless energy. The fuel elements are common, but the usable isotope must be manufactured through a carefully balanced nuclear system. The reaction that consumes tritium also supplies the neutron needed to create more. The plant must therefore maintain a chain of dependence. Plasma performance creates neutrons. Neutrons create tritium. The blanket extracts heat. Processing systems recover fuel. Recovered tritium returns to the plasma. Any prolonged break in this circle can reduce the inventory until operation stops. Success requires the reactor to become its own mine, refinery, furnace, shield, and power source at the same time. Fusion research often appears centered on the plasma because that is where the visible star-like event occurs. Yet the breeding blanket may decide whether that event can continue beyond demonstrations. It has no glow and little public drama. It surrounds the reaction in silence, receiving the particles that escape and turning them into heat and future fuel. The promise of fusion depends on this hidden layer performing well enough for years. A reactor that cannot breed tritium is not truly fueled by abundant resources. It is fueled by a shrinking reserve. Only when the blanket closes the cycle does fusion begin to approach the self-sustaining energy system its advocates describe. The plasma may ignite the process, but the blanket must make the next ignition possible. The most violent part of a deuterium and tritium fusion reactor may not be the plasma that glows at its center, but the invisible storm that leaves it. Most of the reaction's energy is carried by neutrons, particles with no electric charge and therefore no response to the magnetic fields that confine the fuel. They pass outward in straight paths until they strike the surrounding blanket, walls, supports, coolant channels, and structural metals. Each collision transfers energy, changes atomic arrangements, and slowly alters the machine. This is the material problem beneath fusion's elegant image. The plasma can be kept away from solid surfaces, but its neutrons cannot. Every successful reaction sends one of them into the reactor structure, and a power plant would produce an immense, continuous flux. The machine must therefore survive not only heat, but a constant rearrangement of its own matter. When a fast neutron strikes an atom in a metal lattice, it can knock that atom out of place. The displaced atom may collide with others, creating a cascade of damage across a microscopic region. Vacancies appear where atoms once sat. Extra atoms become trapped between normal lattice positions. Over time, these defects accumulate and interact. The metal may harden, become brittle, swell, or lose its ability to carry heat. Some atoms capture neutrons and transform into different elements. Gases such as helium and hydrogen can form inside the material, gathering into tiny bubbles that weaken grain boundaries and encourage cracking. A component that begins as a strong, carefully manufactured alloy gradually becomes something different from what entered the reactor. Its chemistry changes, its internal structure changes, its mechanical behavior changes. The transformation may be slow, but it is relentless while fusion continues. Heat intensifies the difficulty. The inner surfaces of a reactor face steep temperature gradients, repeated thermal cycling, and concentrated loads from escaping plasma. The first wall stands closest to the burning fuel and receives energy from particles, radiation, and neutrons. The diverter, in a magnetic reactor, handles exhaust heat that can be focused into a narrow region. Even without neutron damage, these components would face conditions severe enough to challenge ordinary engineering materials. Under neutron bombardment, their lifetime becomes harder to predict. Heat causes expansion. Cooling causes contraction. Repetition creates fatigue. Irradiation changes how the metal responds to that stress. A surface may erode while the deeper structure becomes brittle. A joint may hold under one set of conditions and fail after years of atomic damage. The reactor must be designed around this aging from the beginning. Materials are chosen not because they remain untouched, but because their changes may be slow enough, predictable enough, and manageable enough to permit useful operation. No material offers perfect resistance. Tungsten is attractive for areas of extreme heat because it has a very high melting point and low erosion under some conditions. Yet tungsten can become brittle, crack under thermal stress, and suffer changes caused by neutron exposure. Steels are strong, familiar, and easier to fabricate, but conventional forms can become highly activated and lose toughness under fusion conditions. Special reduced activation steels are designed so that neutron reactions create fewer long-lived radioactive isotopes, but they still face swelling, embrittlement, and temperature limits. Ceramic and composite materials may tolerate heat or reduce activation, yet they can be difficult to manufacture, join, inspect, and repair. Liquid surfaces could in principle renew themselves after damage, but flowing conductive liquids behave strangely inside powerful magnetic fields and may corrode the structures that contain them. Every material solves one problem while revealing another. The word activation describes a second consequence of neutron exposure. A fusion reactor does not begin with the same long-lived waste as a fission reactor, but neutrons can make structural components radioactive. When atoms absorb neutrons or undergo nuclear reactions, they can become unstable isotopes. The level and duration of this radioactivity depends strongly on the chosen materials. With careful selection, much of the activated structure may decay to lower levels over decades, rather than remaining intensely hazardous across geological time. Even so, large components may require shielding, controlled storage, remote handling, and regulated disposal. Fusion waste is different from spent fission fuel, but it is not absent. The material problem is therefore linked to both maintenance and the long-term environmental case for fusion. A reactor that requires frequent replacement of heavily activated parts may produce a substantial waste stream, even if each piece becomes safer with time. Maintenance becomes especially difficult because humans cannot easily approach the most irradiated regions. Components near the plasma may remain hot and radioactive after shutdown. Repairs must be performed by remote machines operating through limited access points. Robotic arms, articulated tools, transport casks, and automated inspection systems become part of the reactor rather than optional support equipment. A blanket module or diverter cassette may weigh many tons and fit within a tightly packed structure of magnets, pipes, cables, and shielding. Removing it requires precision, replacing it requires alignment, connecting coolant, vacuum, electrical, and diagnostic systems must occur without direct human contact. A repair that is routine in an ordinary power station becomes a carefully choreographed industrial operation. If remote maintenance is slow or unreliable, the reactor may spend too much time offline to be economical. Material lifetime, therefore, affects the price of electricity twice. Components cost money to manufacture, and replacement stops the plant from selling power. A reactor with excellent plasma performance can still fail commercially if its internal parts survive only briefly. Availability, the fraction of time a plant can operate, becomes as important as peak output. A machine that produces enormous power for short periods, but requires long maintenance campaigns, may deliver less annual electricity than a smaller, steadier source. Designers must therefore balance high power density against component life. Increasing neutron flux can make the reactor more compact and productive, but it also accelerates damage. Reducing the flux may extend lifetime but require a larger, more expensive machine. The most efficient physics point may not be the best economic point. Fusion engineering must find a region where the reactor is powerful enough to justify its scale and gentle enough to survive its own success. Testing this balance remains difficult because the exact neutron environment of a deuterium and tritium power plant is unusual. Existing fission reactors and particle accelerators can reproduce some aspects of radiation damage, but not always the same neutron energies, gas production rates, temperature conditions, and mechanical stresses at the same time. Small material samples can reveal important behavior, yet a real component includes welds, joints, coatings, cooling channels, manufacturing defects, and complex shapes. Damage may concentrate at interfaces. Helium may gather near grain boundaries. Thermal stress may interact with radiation in ways that isolated experiments do not capture. Long-term confidence requires dedicated testing, advanced modeling, and eventually years of operating experience. The first generation of fusion plants may therefore function partly as material laboratories, learning how quickly their own structures change. That learning process carries cost and uncertainty. A component predicted to last several years may fail sooner. A new alloy may perform well in small samples but prove difficult to fabricate at industrial scale. A coating may protect a surface until repeated cycling causes it to peel. Fusion's material challenge is not simply to discover a substance that can endure extreme conditions. It is to create an entire supply chain of substances that can be formed, joined, inspected, replaced, recycled, and licensed. The machine must also manage impurities released by erosion. Atoms knocked from the wall can enter the plasma. Even a small concentration of heavy elements can radiate energy strongly and cool the fuel. This creates another feedback between materials and plasma performance. The wall is damaged by the plasma and neutrons. Then the damaged wall can damage the plasma in return. Surface conditioning, magnetic control, diverter design, and cleaning methods all attempt to reduce this exchange. Yet the boundary between plasma and matter remains unavoidable. Fusion must occur in a chamber built from substances that fusion slowly degrades. The reactor's greatest strength, its intense energy release, becomes the source of its aging. There is no sudden catastrophe in this process. The machine changes quietly, collision by collision. Atoms leave their places, new elements appear, gas bubbles grow, cracks begin at scales too small to see. Months or years later, those hidden changes become engineering limits. This slow transformation may decide whether fusion plants operate for decades or become costly devices that spend much of their lives under repair. The challenge is not merely to contain a star-like plasma. It is to build a surrounding world that can endure the particles the plasma sends outward. Fusion succeeds only when the machine survives long enough for its extraordinary physics to become ordinary industry. Fusion is often described as inherently safe because the reaction cannot run away in the same manner as a fission chain reaction. That claim is correct, but it becomes misleading when stretched too far. A fusion reactor does not contain a large mass of fuel capable of sustaining an uncontrolled sequence of reactions after the machinery fails. The plasma depends on narrow conditions of temperature, density, and confinement. If the magnetic field collapses, if the fuel cools, if the vacuum is lost, or if the plasma touches the wall, the reaction rate falls sharply. The fuel expands, loses heat, and fusion stops. In this sense, the machine is self-limiting. Failure interrupts the reaction instead of accelerating it. There is no equivalent of a fission core continuing to release decay heat after an uncontrolled shutdown, and there is no large chain reaction waiting to grow. This distinction gives fusion a real safety advantage. Yet a reactor can stop fusing and still remain dangerous. The plant contains powerful magnets, cryogenic systems, high electrical currents, radioactive tritium, activated structures, hot coolant, vacuum vessels, and components storing enormous amounts of energy. The end of the plasma reaction does not erase those hazards. Safety therefore depends on understanding two different questions. The first asks whether fusion itself can become uncontrollable. The answer is largely no. The second asks whether a fusion power plant can experience serious industrial or radiological accidents. The answer is yes, although the likely form and scale differ from those associated with conventional nuclear fission. The plasma contains only a small amount of fuel at any one time. In a magnetic reactor, the actively burning inventory may be measured in grams or less, spread through a large volume at extremely low density compared with air. If confinement fails, that fuel does not remain in a compact critical mass. It cools almost instantly, in an inertial system. Each target contains only a tiny quantity of fuel, and each reaction ends as the capsule disassembles. These features remove a self-sustaining power surge and limit the immediate energy available in the fuel. A disruption can still release thermal and magnetic energy into reactor components, but the event is an engineering accident rather than a nuclear runaway. The most visible safety claim for fusion is therefore valid. The machine cannot become a star that continues burning after control is lost. The star-like conditions exist only because control is constantly maintained. Once that control disappears, so does the burn. Tritium creates a more persistent concern. As a radioactive form of hydrogen, it can move through systems, enter metals, combine with oxygen, and form tritiated water. Chemically, tritiated water behaves much like ordinary water, which allows it to spread through pipes, air, surfaces, and biological systems. Its radiation does not travel far through external material, but it becomes more important if tritium enters the body through breathing, food, or water. A fusion plant must therefore account for every part of its tritium inventory, from storage and fueling to exhaust processing, breeding blankets, maintenance tools, and waste streams. Because the fuel cycle continually recovers and recirculates tritium, the total quantity in the plant can be much larger than the amount burning in the plasma at a single moment. Containment relies on multiple barriers: ventilation, monitoring, cleanup systems, and barriers that slow hydrogen movement. Even with these measures, small routine releases may occur, and a damaged component could release more. The consequence would depend on the amount, chemical form, location, and response. Fusion does not remove radioactive fuel from the safety problem. It changes the fuel from a solid mass inside a core into a mobile isotope moving through a complex industrial network. Fire can make this problem worse. Tritium stored in metal beds, processing equipment, or contaminated surfaces can be released if structures heat or burn. A fire may also damage seals, cables, filters, and monitoring systems. The plant therefore requires fire protection not only for ordinary industrial reasons, but also to prevent radioactive material from spreading. Similar attention applies to coolant accidents. If a cooling circuit breaks, hot fluid can enter regions under vacuum, creating rapid pressure changes. Water can react with certain metals or with hot surfaces. Liquid metal coolants may introduce chemical hazards of their own. Molten salts can freeze in pipes or corrode structures. Helium gas avoids some chemical risks but operates under pressure and may demand large pumping systems. Each reactor concept rearranges the accident possibilities. None removes them. Safety analysis must follow the actual materials and energy stores of the chosen design, rather than relying on the general statement that fusion stops when confinement fails. The superconducting magnets contain another source of stored energy. Large magnetic fields require immense currents, and the magnets experience powerful mechanical forces while operating. If part of a superconducting coil loses its superconducting state, electrical resistance appears and produces heat. This event, called a quench, can spread rapidly through the coil. Protection systems must detect it and safely discharge the magnetic energy. A poorly managed quench could damage the magnet, insulation, supports, and nearby equipment. The cryogenic fluids used to cool the coils also create hazards. A sudden release of very cold helium can displace oxygen, cause pressure buildup, and make materials brittle. These are not nuclear reactions. But they belong to the safety reality of a plant built around extreme temperature differences and large stored energies. The reactor is safer in one dimension while remaining demanding in many others. Radioactive waste also requires careful language. Fusion does not produce spent fuel containing the same mixture of long-lived fission products and heavy transuranic elements found in conventional nuclear reactors. The helium formed by deuterium and tritium fusion is stable, yet the fast neutrons activate surrounding materials by changing some nuclei into radioactive forms. First walls, divertors, breeding blankets, supports, and shielding can all become activated. Their radioactivity depends on composition and neutron exposure. With specially selected low-activation materials, much of this waste may decay to levels that permit recycling or less restrictive handling within decades or centuries rather than remaining hazardous across geological timescales. That is a meaningful improvement. But it is not the absence of waste. Large volumes of metal and ceramic components may need remote removal, shielded storage, processing, and eventual disposal. Frequent replacement could increase the total amount. The waste burden therefore depends strongly on how long components survive and whether activated materials can be recycled into new reactor parts. A fusion industry with durable components may produce a manageable stream. One with short component lifetimes may create a large and continuous flow of radioactive machinery. Accident scenarios also involve decay heat, although at a lower level than in a fission core. Activated materials continue releasing heat after shutdown, and some reactor structures may retain substantial thermal energy. Cooling systems may still be needed to prevent overheating or damage. The plant must survive loss of power, loss of coolant, earthquakes, flooding, and other external events without releasing significant radioactive material. The absence of a chain reaction simplifies this task, but it does not make passive safety automatic. Designers must limit inventories, arrange natural heat removal where possible, separate vulnerable systems, and ensure that failures do not combine into larger ones. A broken coolant line should not disable tritium confinement. A magnet fault should not prevent emergency ventilation. A fire should not spread through all control systems. Fusion safety is therefore built through layers, not through one reassuring physical fact. Public acceptance may depend on this distinction. Fusion is often presented as nuclear energy, without the dangers that shaped fear of fission. That comparison can attract support, but exaggerated claims can later create distrust. A more accurate description is that fusion removes several of the most severe accident mechanisms while retaining radiological and industrial hazards that require serious control. It avoids a self-sustaining meltdown. It reduces the amount of active fuel in the reaction chamber. It can limit long-lived waste through material choices. At the same time, it handles tritium, produces activated components, operates powerful magnets, and concentrates heat inside complex machinery. Safer does not mean harmless, and safety must be demonstrated through operation rather than inferred from principle alone. The likely failures of fusion are therefore quieter than the image of an exploding star. A plasma pulse may collapse, a wall may crack, tritium may enter a coolant loop, a magnet may quench, a blanket module may leak, a fire may spread contamination through a service area. Most such events can be designed to remain local and manageable, but only if the plant assumes they are possible. The central reaction offers an unusual gift when control is lost. The nuclear fire goes out. The rest of the machine must be designed so that everything around that extinguished fire also moves towards safety. That is the true standard. Fusion earns its safety promise not because nothing can fail, but because failure need not become catastrophe. Fusion enters the public imagination through physics, but it will enter the electrical grid only through economics. A reactor can achieve extraordinary temperatures, confine plasma, breed fuel, survive neutron damage, and still fail if the electricity it produces costs more than competing sources. This is where the promise of star power meets the ledger. Fusion plants are not expected to be simple machines. They require magnets, vacuum chambers, cryogenic systems, heating equipment, breeding blankets, shielding, remote maintenance, tritium processing, cooling loops, turbines, control systems, and buildings designed around radiation and heavy industrial loads. Each subsystem adds capital cost before a single unit of electricity is sold. A project may therefore succeed scientifically while remaining too expensive to build in large numbers. The economic question is whether the complete plant can produce dependable electricity at a price that justifies its risk, construction time, and immense capital. Large fusion programs already reveal how difficult this may be. Research machines are often built as unique international projects, with components designed by different institutions, manufactured across several countries, and assembled to tolerances rarely required in ordinary power stations. Such cooperation spreads cost and expertise, but can slow decisions, complicate supply chains, and make redesigns difficult. When a major component changes, the effect can travel through the entire machine. A stronger magnet may require new supports, a thicker shield may enlarge the reactor, a different blanket may alter coolant systems, maintenance routes, and tritium processing. Fusion devices are tightly coupled, so late discoveries can become expensive. Cost overruns and delays do not necessarily prove that commercial fusion is impossible, because experimental machines are built to learn rather than to earn. Yet they show how unforgiving the engineering becomes when almost every part operates near a physical limit. Construction time matters because energy markets do not remain still. While a reactor is being designed and built, the price of solar panels, batteries, wind turbines, transmission equipment, and other technologies may continue to change. A fusion plant planned under one set of assumptions may enter service in a very different market. If competing sources become cheaper and faster to deploy, fusion must offer something more than low fuel cost. It may need exceptional reliability, compact land use, firm output, high temperature heat, or a role in regions where other resources are limited. The longer construction takes, the greater the financial risk. Borrowed money accumulates interest. Investors wait longer for revenue. Political support may change. Regulations may tighten. Suppliers may disappear. A long project can become expensive before technical problems are counted. This is one reason modular energy systems often gain an advantage. A wind or solar project can be built in smaller stages, with part of the capacity producing electricity while the rest is still under construction. A giant fusion plant may require most of its investment before meaningful revenue begins. The cost of capital can therefore become as important as the cost of steel, magnets, and concrete. Advocates hope that commercial fusion plants will be very different from today's research machines. Standardized designs could replace one-off construction. Factories could produce magnets, vacuum vessel sections, blanket modules, and fuel systems in repeated batches. Experience could reduce errors. Private companies often argue that smaller reactors, stronger superconducting magnets, simplified geometries, or alternative confinement concepts can shorten development and lower cost. These possibilities are real, but they remain unproven at the level of a full power station. A component that is cheaper in isolation may shift expense elsewhere. Stronger magnets can reduce reactor size, but they may face greater forces and require advanced materials. Smaller chambers can lower construction cost, but they may concentrate heat and neutron damage. A design with fewer parts may simplify maintenance while demanding tighter control of the plasma. Fusion economics cannot be judged from one appealing feature. The whole machine must be counted. Operating cost may prove just as important as construction. Fusion fuel is often described as cheap because deuterium is abundant and lithium is widely available. Yet raw fuel price is only a small part of the cycle. Tritium must be bred, extracted, purified, stored, monitored, and protected against loss. Internal components must be inspected and replaced. Remote maintenance equipment must operate in radioactive environments. Magnets and cryogenic systems must remain reliable. Pumps, heaters, lasers, and current drive systems consume electricity. Skilled staff must manage nuclear, mechanical, chemical, and electrical hazards. Waste must be packaged and stored. Regulation, security, and decommissioning add further cost. A reactor with inexpensive fuel can still produce expensive electricity if its machinery wears out quickly or spends too much time offline. Availability may become the decisive variable. A power plant earns money only when it operates. If blanket modules, diverters, optical components, or plasma-facing walls require frequent replacement, the plant loses both maintenance cost and generation time. Even a short repair can become lengthy when work must be performed by remote systems through narrow access points. Components may need to cool before removal. Tritium may need to be recovered. Activated parts must travel in shielded containers. New modules must be aligned and connected with great precision. Every day offline reduces annual output. Fusion designs often advertise high theoretical power, yet utilities care about energy delivered across the year. A machine that reaches full output briefly but spends long periods under repair may struggle to repay its construction cost. Reliable maintenance is therefore part of the reactor's economic core. The cost of electricity also depends on how much power the plant uses internally. A fusion reactor may generate a large amount of thermal energy while consuming substantial electricity for magnets, pumps, cooling, heating, lasers, or fuel processing. Gross output can look impressive while net output remains modest. This creates a capital penalty because the plant must build a larger reactor and generator to deliver a smaller amount to the grid. If internal systems consume a large fraction of production, every unit exported carries a larger share of construction and maintenance cost. Efficiency improvements outside the plasma can therefore be as valuable as higher fusion gain inside it. Better lasers, lower cryogenic loads, more efficient current drive, and improved heat conversion may determine whether a technically successful machine becomes an economical one. Fusion must also compete with combinations of technologies rather than with a single rival. Solar and wind are variable, but grids can combine them with storage, transmission, demand management, hydroelectric power, geothermal energy, fission, and flexible generation. The relevant comparison is not fusion against an isolated solar panel on a cloudy day. It is fusion against the cost and performance of an entire low-carbon system. Fusion could offer firm power independent of weather, which may become increasingly valuable as variable renewables expand. It could also provide industrial heat or hydrogen production. Yet those services may be supplied by other technologies as well. The value of fusion will depend on the grid it enters, the region where it is built, and the alternatives available at that time. A reactor does not need to be the cheapest source in every situation, but it must offer enough reliability or strategic value to justify its premium. Public funding adds another layer to the argument. Fusion research competes with other uses of limited money. Every billion directed toward a reactor program cannot be spent at the same time on transmission lines, energy efficiency, climate adaptation, storage, public transport, or proven clean generation. Critics see fusion as a costly wager whose payoff may arrive too late to address urgent emissions. Supporters see public research as insurance against future energy limits and as a source of scientific advances that private markets may not fund alone. Both positions contain a reasonable concern. Immediate technologies must be deployed now, but long-term options also require years of preparation. The debate becomes false when fusion is treated as a replacement for present action, or when present action is used as a reason to end all long-range research. The harder question is how much to invest, for how long, and under what evidence of a progress. Fusion's billion-dollar character is therefore not simply a sign of a waste. It reflects the scale of the challenge and the value of the possible reward. The risk lies in confusing scientific progress with commercial inevitability. A reactor may become one of humanity's greatest technical achievements and still produce electricity too expensively. It may also mature through repetition, standardization, and learning until costs fall in ways that early prototypes cannot reveal. The economic future remains open because no commercial fusion plant has yet established the true price of construction, maintenance, fuel breeding, downtime, and decommissioning together. Physics can show that the reaction works. Engineering can show that a machine survives. Only years of operation can show whether the promise belongs on the grid. Until then, fusion remains a wager measured not only in energy gain, but in money, time, and the opportunity cost of everything built or delayed while the wager continues. Fusion stands at an unusual point in the history of technology. It is no longer a distant idea resting only on theory, because controlled reactions have been produced. Plasmas have reached extraordinary temperatures, magnets have confined them for meaningful periods, and laser targets have crossed thresholds once considered unreachable. At the same time, fusion is not yet an energy industry. No commercial plant supplies routine electricity. No operating fleet has demonstrated reliable tritium breeding, durable materials, affordable maintenance, and competitive power all at once. The debate therefore survives because both sides can point to something real. The breakthrough is real at the level of physics. The failure remains possible at the level of systems, cost, and time. It is a technology caught between proof and usefulness. The question is whether the remaining distance is a normal engineering path or a gulf that keeps widening as each solved problem reveals several more. The strongest case for optimism begins with progress. Fusion research has repeatedly moved conditions that once seemed impossible into the laboratory. Better superconductors allow stronger magnetic fields. More accurate control systems respond to plasma instabilities faster than earlier machines could. Improved lasers deliver energy with greater precision. New materials are designed to resist radiation and reduce long-lived activation. Computer models can follow particle motion, heat flow, and neutron transport in detail that earlier generations could not approach. Private companies now test smaller devices, alternative geometries, pulsed systems, and new magnet technologies. Large public programs continue building the knowledge needed for burning plasmas and integrated reactors. None of these advances guarantees commercial success, but together they show that fusion is not frozen in an endless repetition of the same experiment. Optimism also draws strength from the scale of the possible reward. A functioning fusion industry could provide firm low-carbon power without depending on weather. Fuel needs would be small compared with fossil combustion. Deuterium is widely available, and lithium could support tritium breeding if the fuel cycle can be closed. The reaction cannot run away like a fission chain reaction, and carefully selected materials may reduce the duration of the waste burden. Fusion could support grids with large amounts of wind and solar energy by providing steady output when storage is depleted or seasonal conditions are unfavorable. It could supply heat for industry, power for dense cities, and energy for regions with limited hydroelectric, geothermal, or renewable resources. Even if fusion never becomes the dominant global source, it could occupy valuable roles that justify its complexity. The strongest case for skepticism begins with the same word, integrated. Fusion's separate achievements have not yet become one complete plant. A plasma can perform well while materials fail. A blanket can breed tritium in a model while practical openings reduce the breeding margin. A target can ignite while the laser system consumes far more electricity than the shot produces. A magnet can reach exceptional field strength while the rest of the reactor remains too difficult to maintain. Every subsystem can approach success alone and still fail when joined to the others. Fusion is especially vulnerable to this because its components interact so tightly. Increasing power density may reduce reactor size but accelerate neutron damage. Thicker shielding protects magnets but enlarges the machine. Higher operating temperature improves electrical efficiency, but weakens materials and increases tritium movement. More complex control can stabilize plasma, but add cost and failure points. Skepticism also grows from history. Fusion has often been described as approaching faster than actual power plants have appeared. Timelines shift because experimental milestones are easier to announce than industrial readiness. A record shot may be treated as though a commercial station has nearly arrived, even when the experiment operates under conditions that cannot be repeated rapidly or economically. This gap between scientific language and public expectation creates frustration. When an experiment solves confinement, the fuel cycle remains. When it solves ignition, plant efficiency remains. When it improves gain, durability remains. When it improves durability, construction cost remains. Fusion can always appear close if the nearest threshold is mistaken for the last one. Time may become the harshest judge. Climate change requires rapid reductions in emissions, and many low-carbon technologies already exist. Solar, wind, transmission, storage, efficiency, geothermal energy, hydroelectric power. And nuclear fission can be built now, though each brings its own limitations. Fusion cannot justify delaying those options. A future breakthrough does not reduce present emissions. If commercial fusion arrives only after grids have already transformed, it may enter a world where the most urgent energy gaps have been filled by other systems. It may become a supplement rather than a rescue. The idea of fusion as the single answer to the energy crisis is therefore dangerous, not because fusion lacks value, but because it places an uncertain future above available action. The opposite danger is to treat uncertainty as a reason to abandon the field. Energy systems evolve across generations, and long-term research rarely aligns neatly with immediate political deadlines. Many technologies require sustained work before their value becomes visible. Strong magnets, advanced lasers, radiation-resistant materials, plasma control, robotics. And high-performance computing can produce benefits beyond fusion itself. Ending the effort would remove not only its cost but also its possibility. The wiser judgment does not ask whether fusion deserves unlimited funding or none. It asks what level of investment matches the evidence, what milestones should justify continuation, and how research can proceed without weakening deployment of proven clean energy. This makes fusion a portfolio decision rather than a matter of faith. Public programs can support long-duration research that private investors may avoid. Private companies can test faster designs and accept risks that large international projects cannot. Independent evaluation can separate physical achievement from promotional language. Funding can be tied to transparent progress in plant-relevant areas such as net electrical gain, tritium breeding, component lifetime, maintenance speed, and construction cost. The central measure should gradually move away from the hottest plasma or the largest pulse, and towards the performance of the whole system. A reactor becomes credible when its surrounding machinery begins to look less like a singular experiment and more like an industry that can be repeated. There is also the possibility that fusion succeeds in an unexpected form. The first useful machines may not resemble the dominant designs of the present. They may be smaller, pulsed, more modular, or built around a confinement method now considered secondary. They may serve specialized industrial sites rather than national grids. They may provide neutron sources, research capabilities, or high-temperature heat before they become major electricity producers. Commercial value may arrive gradually instead of through one dramatic transition. The first plants may be expensive and imperfect. Later ones may learn from their failures. Or the first plants may reveal costs that no amount of repetition can overcome. That final possibility cannot be dismissed. Fusion may prove physically elegant and economically unnecessary. It may remain a source of remarkable experiments, scientific knowledge, and engineering advances without becoming a common power technology. A machine can be one of humanity's greatest achievements and still lose in the marketplace. Fusion begins with a reaction of almost unmatched power, but it surrounds that reaction with one of the most complicated industrial systems ever proposed. The central uncertainty is whether the energy density of the nucleus can compensate for the complexity required to reach it. The judgment, therefore, remains open. Fusion is not yet a billion-dollar failure, because the research continues to produce real knowledge and real advances. It is not yet the long-awaited breakthrough, because no complete power system has proved itself outside the laboratory. It exists between those outcomes, carrying evidence for both. Each new record narrows one doubt while leaving the larger test untouched. Each delay strengthens skepticism, while also revealing what the next machine must solve. The pursuit may end with reactors that quietly feed electricity into the grid, their star-like cores hidden behind ordinary walls and routine operation. It may end with a smaller legacy, leaving behind better magnets, better materials, and a clearer understanding of plasma while other technologies power the world. For now, fusion remains a wager on whether precision can replace gravity, whether engineered materials can endure neutron fire, whether a reactor can breed the fuel it consumes, and whether all of this can be done cheaply enough to matter. The dream has moved beyond fantasy, but it has not yet escaped uncertainty. Its final meaning will not be decided by a single flash of plasma, but by whether that flash can become dependable, repeatable, affordable, and ordinary.